Good afternoon, everybody, and welcome. My name is Gordon Smith. I'm a past president of the Southern African Institute of Mining and Metallurgy and currently serve on council. And I'm a founder member of the Environmental, Social, Governance, Sustainability Committee, the ESGS committee, and will be your webinar chair for today's session. The session has two components, the development of technologies for the purification of mine impacted water, and one on green hydrogen. So as a general introduction, when you think about it, the principles of environment, social governance, and sustainability, ESGS, are not new to us as individuals or as an industry, but have assumed a new level of importance to business and society in the wake of extensive climate change, ever widening inequality, and increased economic risk and uncertainty. As an institute, we see it as our mandate to inform, to educate, and convene our members through dialogue and debate on these critical issues. The SIAM Council has approved and brought into being the SIAM ESGS Committee, the mandate of which is to guide, educate, and inform our members of the pillars, tenets, and dimensions of ESGS in mining, and to be seen globally as thought leaders in its progressive evolution for the mining sector. Significantly, in line with the importance of ESG to industry, we have also agreed on full membership of the SIMM now being open to mining industry ESG practitioners, and we welcome them with open arms. Ultimately, ESGS, sustainability, responsible mining, however you want to call it, now needs to achieve the same status as safety and the broadly accepted concept of zero harm and become a fundamental part of our mining DNA, the way we behave as professionals and the way we execute our businesses. In fulfilling our mandate, we have established this ESGS webinar series, and we'll have an annual SIMM journal edition dedicated to ESGS papers, coupled with monthly commentary on ESGS related themes, in addition to the normal conferencing activities. We look forward to your active support and participation in our programs. I'd like to move now to the first topic. And the first topic is on the development of technologies for the purification of mine impacted water. And that subsession, if I can call it that, will be opened and led by Marion Manuel. Marion is Executive Mineralogy at Mintech, and she leads the mineralogy team in unlocking value through mineral science innovation and specialist services in her role. And I would like to pass to Marion now. Marion, if you could please lead the next session and introduce your three speakers. I'll keep an eye on time. Thank you very much.
Great. Good afternoon, everyone. Thank you very much, Gordon. I'd just like to share my screen. So I'm honored to be afforded the opportunity to present to you at the Mine Impact Water Treatment workshop. And I'd like to talk about Mintech's contribution to solving the AMD crisis. So the Mine Water Atlas shows our catchments and major rivers and the commodities mined in the country. Mine impacted water or acid mine drainage typically originates from the coal and gold fields. These areas are rich in pyrite ores, and during mining or post-mining, when ground and surface water come into contact with pyrite, the iron sulfide oxidizes and also leaches any metals present in the ores, producing a stream of highly contaminated water, which is harmful to surrounding aquatic ecosystems and local communities. And these areas are highlighted here in these yellow, red, and gray dots there. Most of South Africa's mine water discharge or acid mine drainage is concentrated around the coal and gold mines. The coal fields or gray dots on the map are estimated to generate about 250 milliliters of AMD a day. The gold mine areas or the yellow dots are estimated to produce about 350 milliliters AMD a day. Much of this water is characterized by elevated levels of sulfate, iron, and low pH. Some of the water is suitable for irrigation purposes, but the water qualities from the vast majority of sites requires treatment before it can be reused or released to the environment. South Africa's mine water can have sulfate concentrations between 1 and 10 grams per liter. But the water from the coal fields that Mintec is particularly focused on typically averages around 3 to 4 grams per liter. It is interesting to note that mines and mine water discharge overlap with some of the most important agricultural areas in South Africa, polluting water resources that could be used for agriculture and putting local communities at risk. Many operational mines have a neutralization or liming plant on site to increase pH and remove iron before discharge to the environment. About 10 years ago, government upgraded 2 existing mine water treatment plants and built a third to treat the water from 3 gold mining basins. These are high-density sludge plants aimed at neutralizing water using lime and precipitating iron and some other metals. But HDS processes do not remove the sulfate, the total dissolved solids, and other salts. Most of the treated water is discharged to the Vaal and Orange River system. One of the most important river systems for water provision to the most densely populated and economically important areas of the country. It is also a vital ecological system. Due to the high sulfate and total dissolved remaining after treatment, fresh water is required to dilute the treated water to prevent long-term damage to the Orange River system. 7 to 10 milliliters of water, clean water is released from the Vaal Dam for every megaliter of treated water discharge. Because we are a water scarce country, the bulk of the water is purchased from the Lesotho Highlands Water Project. Due to recent droughts, this dilution strategy is putting severe pressure on water resources. As this isn't a sustainable strategy for surface water or mine water management, governments see this as a temporary or short-term solution for AMD until there is a better alternative. But there isn't viable, affordable alternatives available. So there is an urgent need in South Africa to develop sustainable technologies for sulfate removal from AMD, primarily to relieve the current pressure on water sources and the environment, and to ensure sustainable mine closure for current operations. So Mintec has expertise in acid mine drainage prediction, metallurgical flow sheet development, which is mostly used for water efficient processes, process optimization and control, and design for zero liquid discharge. Treatment of mine impacted water is an area that we will be focused on today, as well as post-mine closure and land rehabilitation. Mintec has significant water and post-mine closure expertise, and we are ideally positioned to focus on technology scale-up and implementation. Our strategy is an integrated approach to mine closure, mine water management, and mine water treatment. Therefore, we have created a water research program and a post-mine closure strategic program. The overarching vision of our work at Mintec is in the mine water sector, is a toolbox of technologies that can be implemented to solve regional scale water problems, and to identify potential social economic opportunities. I'd like to add here that South Africa has very sophisticated national policies and guidelines which have been carefully designed to address mine, water, and post-mine closure problems. We see there is a springboard to enable and address gaps in implementation. We have also spent considerable amount of time forming partnerships with the mining sector and collaborations in order to secure sufficient funding and to make enough resources available for these endeavors and to de-risk technologies and the R&D as far as we can. But the mine water problem is complex because we have many sites with different volumes of discharge and different qualities. And in the mine coal region, I do want to add that recent estimates that are a total of 350 megaliters per day mine impacted water being discharged from coal fields in Mpumalanga. The areas where Mintec is mainly interested in is looking at the high sodium, calcium, magnesium, and sulfate reduction using membrane desalination, as well as precipitation and lime neutralization, and that is used throughout the pH area from neutral pH to very low pH areas, and then also using biological processes for low calcium, magnesium, and sulfate, but not sodium. For today, we will be having a discussion on Mintec's closure program, our SAVMIN process, and the NICMA process. The closure program will be presented by Kerri, which is a principal scientist at Mintec. She has gained expertise in environmental engineering and management, as well as the treatment of wastewaters using anaerobic processes over the past 15 years. She's also responsible for driving the R&D related to biological treatments of mine water. She's involved in Mintec's water research program and is developing a post-mine closure strategic program for Mintec. The SAVMIN program technology will be shared by Gebhu Ndlovu. He is the head of Environmental Center in the Hydrometallurgy Division at Mintec. He's responsible for research development and innovation activities related to long-term environmental sustainable targets towards a greener future. And lastly, the NICMA program will be presented by Keneiloe Sikhwivhilu. She's a chief scientist at the Advanced Materials Division within Mintec. She has a PhD in chemistry with specialization in catalysis and nanoscience. Part of the study she carried out at the Center of Applied Energy Research, University of Kentucky, and she's obtained a postdoctoral training in nanocomposite filtration membrane development from the University of California, Los Angeles, as a chief scientist at Mintec. She leads research development and innovation activities of nano-enabled filtration membranes and absorbent technologies for application in water and wastewater treatment. I will then hand over to Kerri to discuss the closure program. Thank you.
Kerri, we can't seem to hear you. Just check your connection with your headsets.
Can you hear me now? No?
Yes, we can. Thank you.
Better. Okay, no problem. Sorry about that. So I'm going to talk to you just for a few minutes about our semi-passive treatment technology to treat mine impacted water that we've been developing here at Mintec. Biological processes present an opportunity for sustainable technologies for treatment of mine impacted waters. And as Marion mentioned, our mine impacted waters can have sulfate concentrations up to 10 grams per liter. And the water that we, in my division, have been specifically focused on has sulfate concentrations between 3 and 4 grams per liter. And one biological process that has been shown to successfully treat mine impacted waters containing sulfate is biological sulfate reduction. Mintec has been developing a biological sulfate reduction process for high sulfate mine waters over the past 10 years, and we've trademarked it and named it Closure. Sort of hijacked the Mintec logo there as well. So the process consists of two stages, namely a biological sulfate reduction step to remove sulfate, to increase pH, and to remove metals. A reduction of sulfate results in sulfide, and this can be corrosive to irrigation equipment, and it can pose a safety risk to plant operators. So in the second stage, the focus is on biological removal of sulfide and any residual metals in the water, as well as the recovery of biosulfur. The aim of our process is to produce treated water that's fit for irrigation. Closure is intended for mine sites post-mine closure, and it's suitable for sites with limited infrastructure in remote locations, as well as ownerless and derelict legacy mine sites. The goal of our treatment technology is to produce water that is fit for reuse in irrigated agriculture in order to promote job creation, water and food security for the post-mining economy, and to build resilient communities and protect the receiving environment. So our stage 1 biological sulfate reduction process consists of reactors or ponds with a packed bed, and this provides the support for colonization by a diverse consortium of microbes. These microbes break down any available organic material into simple compounds like volatile fatty acids, and these are the preferred substrate of our sulfate-reducing bacteria. Using an organic source of carbon, such as ethanol or acetate, and using sulfate for respiration, the microbes produce sulfide and bicarbonates, and this drives up the pH of the water, and it produces alkalinity. At the same time, sulfates are removed, and the sulfide that's produced binds to any metals in solution to form a metal precipitate, which is retained as a stable solid in the system. In our second stage, the aim is to cultivate a floating biofilm in order to oxidize all of that sulfur that was produced upstream, to oxidize all the sulfide that was produced upstream to sulfur, and thereby removing the sulfide problem and potentially producing a valuable byproduct. Under chemical and biological conditions, in the presence of high levels of oxygen, sulfide rapidly oxidizes to sulfate. Now we want to avoid this because we've just spent a lot of effort in stage 1 removing all of that sulfate. So when oxygen levels are low, typically less than 5%, and when sulfide concentrations are high, with a sulfide to oxygen molar ratio of 10 to 1, partial oxidation of sulfide occurs to produce elemental sulfur within the biofilm. These conditions also select for sulfur oxidizers, and these are responsible for the production of biosulfur. So this is a picture of our pilot plant that we ran over the past year and a half at the eMalahleni Water Reclamation Plant in partnership with Thungela. And the aim of our project was to produce water that was fit for reuse in irrigation. So this is a shot of our whole pilot plant. It was a very exciting project. This is another angle showing our biological sulfate reduction reactors on the left-hand side, and the sulfide oxidation tank or sulfox tank in the greenhouse on the right-hand side. So we operated two systems. One was a single-stage reactor, which we called RP, which is sitting in the middle of the shot, and a two-stage process, R1 and R2, on the left of the shot. And both of these produced water that we then fed through the sulfide oxidation tank to remove excess sulfide. Our feed water had a pH between 2.5 and 3. And it was then pumped into the green 5,000 litre feed tanks that you can see in the middle of the picture. And then this was fed to our reactors at a rate of 500 litres per day. Each system treated 500 litres per day. And we operated our pilot plant for about 500 days. So this graph shows the sulfate reducing performance of our two biological sulfate reduction systems. Startup for these reactors is 6 months, but last year we had some early winter temperatures and then we went into lockdown, indicated by the gray block. So we didn't quite achieve what we wanted to in the first 6 months. However, once the country opened up after lockdown and once our system had been operated in batch mode for several weeks over lockdown, And with the warmer temperatures in August, we suddenly got really good performance from our systems. So after lockdown, I have divided the period into phases based on the feed sulfate concentrations. For the first 100 days after lockdown, we achieved an average sulfate reduction rate of 233 grams per cube per day. And over December, we experienced elevated feed sulfate concentrations, which meant that sulfate reduction increased to an average of 368 grams per cube per day. And then it decreased again when concentrations returned to normal. Over this whole period, the maximum sulfate reduction rate was 458 grams per cube per day. And we were very excited by these results because in the lab, we achieved between 170 and 190 grams per cube per day sulfate reduction. And in other passive systems, it can be as low as 70 grams per cube per day or even lower. So we were thrilled by these results because it really shows that our process has the potential to treat high sulfate waters. So this is a picture of our sulfide oxidation tank. And on the right-hand side, you can see a picture of the biofilm or the floating film that sits on the surface of the water. After lockdown, our biofilm suddenly began to thicken and it turned white, indicating that that sulfide has been partially oxidized to sulfur. We achieved between 30% and 76% removal of sulfide in this tank. And our biofilm contained up to 60% elemental sulfur by mass. Which was also a fairly exciting result for a pilot scale plant. So unfortunately, we didn't get consistent removal of sulfide, I must be honest, but this has just taken us back to the drawing board where we are considering some design changes to improve the efficiency of this tank. So finally, this table gives you the metals concentrations in the feed water, and then after our water has been treated in the closure process. So the red cells show where the feed water exceeds the Department of Water and Sanitation's target water quality requirements for irrigation. You can see there's only a few metals of concern in the water, being aluminium, iron, manganese, nickel, and zinc. After treatment in both stages of our process, the water met all of the Department of Water and Sanitation's irrigation requirements for metals, which you can see in the green cells, except for manganese. We also had a period where our iron concentration was extremely high, above 1,000 milligrams per liter, and our effluent iron concentration was still around 0.3 milligrams per liter during that period. In the second table, you can see that during the process, we removed 98% of the sulfate, we increased our pH to around neutral, and we increased the alkalinity of the water. Now, the nutrients in the treated water are higher than the target water quality requirements. This suggests that further optimization of the nutrients is required as we scale up. We are consulting with our partners at the University of Pretoria, and they're doing a more detailed analysis of the water quality using the decision support system model. And this takes into account rainfall, soil type, crop type, and it tends to be a little bit more lenient on parameters like manganese, alkalinity, electrical conductivity, and the nutrients. So we are eagerly awaiting those results. Essentially, while we piloted, we achieved very high rates of sulfate reduction. We increased the pH of the water and we removed all metals except manganese. And the major water quality parameters meet the Department of Water and Sanitation targets for irrigation quality water. Going forward, we are scaling up our process. This is a picture of the demonstration plant that we've just constructed. We've received funding from the Technology Innovation Agency, and we formed a consortium with our partners Thungela, the Moss Group, and the University of Pretoria. Thungela have funded and constructed this plant at the eMalahleni Water Reclamation Plant, and Mintech is also funding operation of the plant. The aim is to demonstrate the closure technology at 50 cubes of acid mine drainage per day, and then to develop design parameters for a commercial scale plant at a mine site. University of Pretoria will also use the treated water from this plant for crop trials to demonstrate the integration of this treatment process with irrigated agriculture. So we are quite excited about working on this technology going forward. And that's all for me. Thank you for listening. And Gebhu, it's over to you.
Gebhu, if you're trying to talk, you're on mute.
Am I still on mute?
We can hear you now. Thank you.
Oh, okay. Thank you. Good afternoon, colleagues. I will be presenting some key aspects of the segment technology for mine impacted water treatment. Now, even though the segment process was developed by Mintech in the 1990s, there has been continuous improvements made over the years in order to improve the CapEx and OpEx of the segment process. Just before we delve deep into the nitty-gritty of how the segment process works, let's quickly take a look at some key technological applications and benefits of the segment technology. Now, some of the targeted applications include the treatment of AMD with low pH and contain metals and sulfates. The process can also treat MIW water to produce water that is fit for purpose. This can be irrigation or crops, forage, as my colleague Kerri has mentioned. It can also, the water, all that is treated can also be water that was pre-treated using lime precipitation to remove metals, but still contains high concentrations of sulfates. The process can then remove the remaining sulfates from the water. Now, some of the major benefits of the process is that it can treat various wastewater streams and is not limited by the concentration of pollutants. The process can also reduce sulfate concentration to less than 200 milligram per liter and can be used to recover metals of interest. With the segment process, one can also generate or regenerate and recycle key reagents such as aluminum hydroxide, therefore limiting the operating costs associated with fresh reagent addition. Given that the process is operated at ambient temperature and pressure, it means it consumes less electricity, which makes it viable for the current market at which we operate. The process itself can be described as a four-stage precipitation-based process for the treatment of mining impacted water. In the first stage of the process, the high concentrations of calcium and sulfate in solution induces the precipitation of gypsum. Therefore, the solution leaving stage 1 is saturated in calcium sulfate. The combined metal hydroxides and gypsum solids are separated from the solution and leave the process as waste. In the second stage of the process, aluminum hydroxide is added to the gypsum saturated solution. This results, therefore, in the removal of calcium and sulfate from the solution by the formation of an insoluble calcium aluminum sulfate salt called Endowment. Now, the solution from stage 2, which contains low concentrations of sulfate, is treated with carbon dioxide in stage 3 of the process. These then lower the pH and precipitate calcium. Thereafter, calcium carbonate is then separated from the treated water, leaving behind clean water, which we consider potable. On the fourth stage of the process, aluminum hydroxide, which is a key reagent for the process, is then recovered and recycled back to stage 2 of the process. From this schematic, it should be noted that the ability to recycle the key reagents is what enhances the economic viability of the segment process. Just a quick recap as to why the development of this type of turnkey technologies is of paramount importance for the country as a whole. It is well known that AMD plants that are operated on the central, eastern, and western basins involve lime neutralization. The treated water from these plants still contains sulfate at its saturation limit, which is around 1,500 milligrams per liter. And at these concentrations of sulfates, the water is not safe for environmental discharge or human consumption. This is now where the segment process can play a crucial role in further treatment of the water and removal of sulfates to concentrations below the South African national standard for drinking water, which is below 200 milligrams per liter. For demonstration purposes, the segment pilot plant was installed at Stillwater in Randfontein. The plant is capable of treating about 4 cubic meters per hour of AMD to produce potable water. As I mentioned earlier, that we are targeting the removal of sulfates from about 1,500 to less than 200 milligrams per liter, as per SANA's requirements. Through the development of a front-end engineering design pack, as Mintech, we can now safely say and confidently say so that we have a wastewater treatment technology which has been proven through successful operations in the relevant operating environment. And the technology is now ready for full commercial deployment. The technology, as I mentioned earlier, has capability to treat AMD water to potable. Other than the submarine technology, we also, as Mintech, re-established our expertise with the NIM6 technology. The NIM6 technology is a continuous multi-stage ion exchange column used to recover aluminum from dilute solutions. The column can treat solutions containing suspended solids and can be operated over a wide range of feed states, feed rates, and concentrations. Some of the advantages of this technology is that the resin losses are quite low, while the efficiency of recovery is very high. The technology has low capex and opex, which makes it feasible for those that are interested in actually removing uranium. Also, if you want to remove rare earths, as it seems like there's an uptake now when it comes to recovery of rare earths. So these technologies, they come into play. And thank you, that's all from my side. Over to you, Keneiloe.
All right, good afternoon, everyone. Thank you, Gebhu. Yes, my name is Sikhwivhilu, and I'm going to share with you. Am I audible? Can somebody please confirm if I'm audible?
Yes, you are.
Thank you. Yes, I'm going to share with you the work that we do in our advanced materials division regarding mine impacted water treatment. In the advanced materials division, which is situated within Mintech, we use advanced materials to develop various technological solutions for water remediation. These materials are basically materials that are specifically engineered to exhibit novel and enhanced properties that confer superior performance relative to conventional materials. And our advanced materials are nanotechnology based. And the kind of technologies that we're developing from these materials are basically adsorptive technologies, which are mainly for solid phase remediation. These are mainly our nano adsorbents and also chelating nanocomposite materials for removal of heavy metals and organics in water. We also develop photocatalytic technologies for the degradation of chemical pollutants in water. Antimicrobial technologies for degradation and removal of pathogens, viruses, bacteria in water. But this is particularly important for drinking water production. And last but not least, it's filtration membranes for liquid-solid separations. We basically use South African minerals as enablers to provide bespoke solutions to the South African market. So now the following slides will focus on the technologies that are mainly useful for remediation of mine impacted waters, which are the ones that are highlighted here, the adsorptive technologies and also the filtration membrane. Our nano-enhanced chelating adsorbents are developed specifically for removal of heavy metals and also organic pollutants. These are materials that have high specific surface areas. They've got high adsorptive rates. They are regenerable and reusable, and this is very important, particularly for the South African market, to ensure that the cost of running these particular technologies is brought down as much as possible. These are not ion exchange adsorbents, but they are basically, therefore that means that there is no exchange of any ions into the solution that one is trying to remove pollutants out of. Therefore, this results in high quality water, which can be suitable for drinking. So basically we're developing them mainly for potable water production from impacted water. The kind of heavy metals that one is able to remove with them include chromium 6, lead, zinc, cadmium, cobalt, and a whole variety of other metals. Currently, the membranes are still under development, and we are hoping that industry could partner with us so we can be able to optimize these resins accordingly for the South African market. The next technology is the nano-enhanced low-fouling ultrafiltration membrane, which we have branded NICMA membrane. Basically, a membrane is simply a semi-permeable barrier that operates via size exclusion, wherein it separates solutions from solutes via a sieving mechanism. That is, anything that is bigger than the pores of the membrane gets blocked off, while anything that is smaller than the pores of the membrane passes through. So now the NICMA membrane is an ultrafiltration membrane and is internally skinned, and therefore it operates on an inside-out filtration mode, which makes it ideal to produce high-quality product water from treated effluent. This membrane, it removes your suspended solids, colloids, viruses, and bacteria in water. And the process can actually even be enhanced by addition of micelles to remove particulates that are not ordinarily removed by ultrafiltration membranes to produce high quality drinking water that is of RO quality without the high energy requirements associated with the reverse osmosis process. So the membrane was basically designed to be low fouling because it contains hydrophilic surface groups and also nanomaterials that make it hydrophilic. And this enables the membrane to be operate for longer periods without a need for chemical cleaning or even backwashing using product water, which makes eventually the membrane to be energy efficient and requires a lower operational cost. Like any membrane technology, it has a small footprint and allows for compact containerized treatment plants to be made from it, and which allow for ease of deployment to sites where interventions are required. The NICMA ultrafiltration membrane has been demonstrated on, has been assessed for the treatment of various mine effluents from the coal mining operations, gold, and also PGM mining operations, for possible recycling and reuse of the water. The assessment of the technology was done based on the productivity and the quality of the treated water. The membrane showed an over 95% reduction in the turbidity of the effluent to less than 1 NTUs and a constant productivity over a period of 4 months without a need for chemical cleaning, with a backflush done only once a week, which is way better than what commercially available ultrafiltration membranes can offer. A single NICMA ultrafiltration membrane module, which is 1.2 meters long, has a surface area of 7 square meters. It can produce 2,500 liters of treated water per day. And these membrane modules can actually be stacked up to treat larger volumes of water. So the membrane is under development. We've conducted internal demonstrations of this membrane. And now what is outstanding is external validation. So internal validations, now we are left with external validations in a relevant environment. And we are hoping that we can be able to get an industry partner to allow that to happen. The NICMA membrane, together with the submarine enclosure technologies, have been demonstrated at pilot scale as an integrated solution for mine-impacted treatment, mine-impacted water treatment at pilot scale with great success, as covered in detail by Mining Review Africa in 2018. These technologies are at the forefront of developing long-term environmental sustainability targets towards a greener future. Now, these 3 technologies that we've presented today, we believe that they are suitable for treatment of acid mine drainage and also mine-impacted water for reuse in non-potable applications, such as for reuse in industry, for industrial operations, or even back into the mining operations. They can be used for irrigation of food and also energy crops, talking to Sustainable Development Goals 2, which is food security, Sustainable Development Goal 7, which is clean energy. They can be used, the water can be used also for afforestation and oil recreation, as well as the treated water can be used for potable applications, specifically with the NICMA membrane technology. These solutions could also be integrated depending on the desired end use and mine water and also the wastewater quality. So basically, one can be able to address the Sustainable Development Goal 6, which is increasing availability of clean water, minimizing pollution, and also SDG 3, which is improving the general health of the population. So in general, to conclude, we feel that our mine impacted water solutions are aimed at recovering the most valuable component of our waste and mine waters, which is the water itself, with the goal of providing a value resource to local communities and hopefully paving the way for socio-economic development. Now, in closing, as Mintech, we are seeking partnership opportunities with the mining, with industry and the mining sector in order to play a part in contributing towards the country fulfilling the National Development Plan Goals 2030 and also the Sustainable Development Goal 30 around water resource management. Also to ensure that we provide relevant and appropriate solutions to existing challenges encountered in mine impacted water management. We believe that these partnerships can provide Mintech with, can make sure that Mintech stays relevant to the market needs, that it helps us so that we can also be able to provide and conduct market pull research development and innovation projects. We will also need access to wastewaters for us to continue to do our research development and innovation activities that are aligned. And we can also be able to get access to pilot or demonstration sites for us to be able to conduct external validations and during our product development. And lastly, but not least, the benefit that Mintech is hoping to get out of these partnerships is to make sure that we are hoping that we'll be able to get eventual uptake of these technological products by industry, because otherwise our research development and innovation activities will be futile. In terms of the benefits for the mining industry partnerships, for the partners themselves, when they partner with Mintech, they will get a strong R&D partner, they will get access to technical information, and Mintech will be your source of new technologies to address emerging challenges. And last but not least, the mining industry can be able to get solutions that are bespoke to their unique challenges instead of taking solutions that are off the shelves that have been optimized for challenges that are experienced in other parts of the world and not necessarily here in South Africa. And with that, I thank you all for your attention.
Great, thank you very much. A big thank you to Marion, Kerri, Gebhu, and Keneiloe. What I'm getting from this, and by the way, thank you very much on time. I was getting a bit concerned in the beginning that we were going to struggle to finish on time, but we are slap on time, perfect for the Q&A session, which I'd like to just throw in an opening sort of perspective, which hopefully will open up something from the attendees on this particular session. I listen to this and I say to myself, what an incredible portfolio or suite of technology options to deal with mine impacted water. And the kind of questions that went through my mind, and perhaps Marion, you could guide who could address these, and it could open up some of the conversation, is so what are the thoughts on deployment in terms of distributed treatment plants versus centralized plants? If you're looking at 350 megaliters a day from the coal industry, and we haven't even spoken about the rest, the gold and the PGM, scaling is an important perspective. The other thought which crossed my mind was circular economy, very important in terms of sustainability, was to understand what are the opportunities around the discharges, I won't call them wastes, discharges from these various plants. For example, the gypsum and calcium carbonate. I'm quite familiar with the RO plant in Mpumalanga, so have a view on that. And then nobody spoke about capital and operating cost. So the three things in my mind were, how ready are we as an industry to adopt some of this technology, and what's the logic behind deployment? Can we tie in the circular economy logic? And the third is capital and operating cost. And I hope that would stimulate a few questions on the Q&A, whilst Marion, perhaps you would like to guide some response to my queries. We've got a few minutes to have Q&A. I've lost you, Marion. There we go.
Hi, Gordon. Thank you very much for those questions. Yeah, we definitely need to think about those. Kerri has just indicated that she'd like to respond to one of those questions regarding the coal treatment.
Thanks, Kerri. Kerri, you're maybe on mute again. I'm looking for your profile on the list, but we're not hearing you.
Yeah.
Kerri,
Can you hear me now?
yes, go for it. We've lost you again, unless you're taking a very deep breath. No, we can't hear you.
Okay, I'm here now. Apologies for that. I'm using Marion's laptop.
Right, now we can hear you. Go.
Yeah. So what I wanted to say was that regarding your point about the volumes of water, obviously the coal mine regions are different to the gold mining regions because the gold mining basins are all linked. So that becomes one large volume of water that would probably need a different strategy to address. Whereas where we are working in the coal mining regions, a lot of those sources are point sources. Some of them are very low flows, less than 0.5 megaliter a day, and some of them are really high flows, 14 to 20 megaliters a day. So I think our philosophy at Mintech is that there should be a larger toolbox of solutions for treatment of mine water. And because we have different chemistries, we've got different volumes coming out, we've got different sites. Some sites have electricity, some sites don't. So I think the idea is that we have as many different solutions as possible to tackle the different kinds of problems that you find in different regions. Some sites might have a site-specific solution, others might require a more regional approach, like with the gold mining region. So yeah, I think from our perspective, the idea is just to get as many of these technologies available for treatment of the different chemistries, and then we adapt them using our engineering expertise to the different kinds of problems that we find at the actual mine sites and point sources.
Kerri, thanks very much. I've just looked up on the screen here and I can see that we've got a number of questions in the Q&A. I'm in the chat at the moment, so I'm just going to deal with the chat question. There's a question here around, are these technologies currently used in industry? So what's the level of adoption? And then proof on an industry scale. I think that was part of my scale-up question. And then similar to my concern about, what about cost? Do you have any perspective on cost? If we could briefly answer that one, Marion, from your team, and then I'll move to the 4 questions in the Q&A.
Okay, I've stolen Marion's laptop, so I'm going to continue to steal the limelight. I think, Keneiloe, you can jump in and help me with your membrane-related technologies. But in terms of biological sulfate reduction, is actually used across the world. But it tends to be used with water that has got much lower sulfate concentrations, between like 250 and 350 milligrams per liter of sulfate. And the idea is that we reduce just enough sulfate to produce sulfide to precipitate out any metals. And you find in Europe and America, the concentrations of metals in the mine waters are much higher than we experience here. So what we are trying to do is the other way around, is try to remove that sulfate, and along the way, we remove those trace amounts of metals that we have. But no, this technology is not really used in South Africa. There is one plant that's run by Tungela in Vryheid. And they're also trying to remove just enough sulfate that they increase the pH of the water. So we do have one commercial scale plant in the country, but in terms of biological sulfate reduction, we're trying to do something slightly different and recover the sulfur from the water. So ours is on its way, let's say that, to being used in the industry. Keneiloe, I don't know if you can talk about yours.
Yes, regarding membrane technology, there is nothing really new about membrane technology to begin with. Membranes have been used, I think, since the 1960s for treatment of various types of waters. And but now the problem now is that I think the membrane uptake in general in the country is not picking up at a pace at which it's supposed to, because of the various challenges that are encountered with membrane technology. which is the issue of the fouling, which increases the operating cost of the membrane, because once the membrane fouls, there's a lot of chemical cleaning that needs to be done. There is a lot of backwashing with clean water to be done. And also another problem is the issue of energy requirements. Now, the option that we are bringing with us, with the membranes that we are developing here, is that we are trying to minimize on those problems to make sure that there is a membrane, or membrane can become a technology of choice, can be easily become a technology of choice in this country, mainly because we have issues with water to begin with. And without membrane technology, the scope is limited as to how much or how clean can one be able to treat the water, so that it finds more applications, particularly for potable applications, that is drinking water applications. And now, and another thing also is that in the whole country, or in the whole continent, there's not even a single membrane that has that is manufactured in the country to begin with, or even in the continent. So we are bringing in an option which is specifically tailored for the South African market. That's what we are doing. Is our membrane already being used in the industry? Not yet. We are still on product development. That is the reason why I highlighted the issue that we still need to conduct external validations, so that we can be able to optimize the membrane for a specific process, so that we can be able to offer those solutions to the market.
Great. Thank you very much. We've got a few minutes left. I want to go to the questions in the Q&A. And I think these can be answered briefly, please, if we could. Sam has a question about what's the resident time of each process step? I think he's thinking around how do we scale this up appropriately, but what's the residence time of a typical process? Maybe Kerri, you would talk about your sulfate one.
Yes, I did see that question. So we have targeted quite long residence times. In our pilot plant, we were doing 10 days residence time. And obviously at demonstration, we will try to reduce that. We've managed to do 6 days in the lab, but it's really long because out in the field, when you can't heat your bugs, you need to, If you have longer residence times, then if you have environmental fluctuations like temperature or varying flows or that kind of thing, they can actually tolerate the variability quite a lot better than if you really try to push them with those faster residence times. So yeah, it is slow, and we will try to get it more efficient, but it's slow. Passive processes are very slow. Anaerobic processes are very slow.
Understood, and that relates back to the scale-up and deployment challenges. I hear you on that. Another question from Alfred is around sludge generation from backwashing of all of these processes, because invariably, I don't like to call them wastes. I think they're opportunities into the circular economy, but we're taking stuff out of dirty water, if I can call it that. So how is that material handled? Because it's bound to be toxic in some respects, the heavy metals, apart from being potentially corrosive.
I will quickly say one sentence on biological sulfate reduction, and I'll have to hand over to Keneiloe and Gebhu just to give one sentence on their technologies. In terms of biological sulfate reduction, our sulfides bind to the metals and they produce a metal sulfide precipitate. And thus far, they tend to be retained in the bed. Because we have such low concentrations of metals in our water, we haven't experienced any excess buildup of these metals. So from the biological process, we actually haven't produced any solid waste, except for our biofilm, which we think is a byproduct at this stage. But I'll get Keneiloe and Gebhu to jump in on their technologies.
All right, the good thing about passive membrane technology is that one is able to produce a retentate that is not one does not produce sludge. Let me just say that, yeah, one does not produce sludge, and one can even be able to mine or to extract valuable minerals from the retentate that is generated by the process. So there really is no sludge to treat.
Okay.
From my side, other than the fact that we produce actually high quality gypsum as waste, but it can be taken up by different industries for application. We also, the metal hydroxide that we produce as considered waste, actually that is where we can extract some value, because the metal of interest can be taken off from that material that is considered waste. Thank you.
Yeah, well, thanks very much. May I see your question covers, to read it out, an exciting range of options. Is it possible to reflect on the pros and cons of each process? I think we've covered some of that. I would like to stop here, May, unless you've got anything in particular that you would like tackled rather than a generic response.
Hi, Gordon. I'd just like to include, just the discussion around sludge and, the circular economy. I'm currently working on a study looking at hyperaccumulator plants to extract metal, so from tailings dams. So there would then also be opportunity in looking at any waste from the Savman project, any sludge that's created there as well. And use those very similar hyperaccumulator plants to extract metal. So that is a project that we are currently working on at Mintech, and that may be able to respond to those questions.
Thank you. So I'm going to stop us there so we don't run over time. We're 1 minute into the next session. I just think as a principle, and part of what I was outlining in the front, is to get our thinking to move away from wastes and say they input products. We just need the process to convert those products into something of value to somebody else. That's the essence of sustainability. There is no waste. Whatever output from one process, if it's not used directly for something, it becomes an input to another process. So just a thought to leave with you. Right, let's move on. And thank you very much to the Mintech team. Really appreciate that. I'm going to move now across to the second topic, which is on green hydrogen. And this topic is going to be spoken to by Quintin Hobbs. Quintin is a partner from EY, and he leads the EY strategy and transaction service line for EY in Africa. He's based in Johannesburg and leads a team of almost 400 transaction and strategy professionals across the continent. He's a chartered accountant. As an engineer, I'll have to forgive him that, and a CFA, and has over 2 decades of corporate finance experience, focusing mainly on infrastructure, natural resources, and mining sectors. So here we have the financial, the economic perspective being brought into a very real part of dealing with climate change and new energy sources in the world. Quintin, could I hand over to you? I'm going to go quiet now. Thank you.
Great, Gordon. Thank you very much. And good afternoon, everyone. Great to be with you. And yes, I do realize the irony of a finance professional talking about science to a group of scientists. So, but I think as you've mentioned, I'm bringing in a lot of the economics there. So as we've said, EY have done quite a lot of work and modeling globally around this new industry. So green hydrogen, what is the outlook for the industry? What is it all about? So I'm going to share my presentation and start off by saying this has really sparked an interest in me to be a bit of an amateur chemist. And so we are at the point where we are going through a fifth energy transition in human history. So a very exciting time to be alive. And there is consensus that this fifth energy transition is moving us from fossil fuels in the form of mainly crude oil into renewable energy and renewable energy electricity. Now, the key part here is you obviously can't store electrons. And so chemically, how do you store the energy for later use and to be usable? And so if you listen to Elon Musk and you ascribe to his point of view, the answer is lithium-ion batteries. And that's the one-size-fits-all approach to storing this fantastically cheap energy source from PV and wind. The other school of thought is, well, hydrogen. Hydrogen is the molecule that we do that. And I'm going to talk to you a little bit about how it's probably not that simple, and it's probably a combination of the two. And with hydrogen, we also include ammonia as a more stable molecule that we can use to store this energy. And so I'm going to talk a little bit about the decarbonization potential here. And so using really hydrogen as an energy vector and an industrial feedstock. And so producing it from, as we said, low carbon sources such as renewable energy. I think there is a lot of concern about greenwashing. And so you'll hear about all the different colors of hydrogen, pink hydrogen, blue hydrogen. But there is consensus that the gold standard is hydrogen produced directly from renewable energy such as wind and PV. And so here's a little bit about where we can use it to decarbonize different applications. And so the checked out blocks is where we think the hydrogen is the main solution for that area. So really around as a feedstock for the industrial uses of steel and chemicals, where we can replace the likes of coking coal and natural gas as an energy molecule and a reductant. So the other real low-hanging fruit is long-distance transport, so aviation, shipping, etc., where green hydrogen is probably more suited than lithium-ion batteries, and we've talked about as a feedstock. And so in South Africa, we have a long heritage of producing hydrogen, in this case, grey hydrogen, as a feedstock for the likes of other petrochemical products. The issue is around really where will the technology evolution for these two competing technologies play out. And so will we see advances in lithium-ion battery technologies, or will they stagnate like we've seen? We've been promised advances in lithium-ion battery technologies for the past, I don't know, 10, 15 years, but my battery in my cell phone is still pretty much the same battery that it was 10, 15 years ago. And so fascinating to see how this technology arms race develops. So here's a little bit of a graphical representation around where this demand is going to come from. And so we really do think there is a large market potential here. And we'll talk a little bit about what's driving the move towards this. But really, the major opportunity is, as we've said, in final consumption, so cement, steel, chemicals, other industrials, transport as a major application. And so probably more in the heavy duty transport, shipping and aviation, where we think green hydrogen has a strong role to play. And then as well as a dispatchable power generation and storage, a storage molecule. And so during peak times, or sorry, during off-peak times, being able to run these large gigafactories and store it, and then have it ready for dispatch through either a fuel cell or a turbine engine, where you're putting hydrogen or ammonia in, and using that as a peaking or mid-merit power generation mechanism. So these are all the colors, and so a little bit of a crash course around the different types of hydrogen. Obviously, it's all the same hydrogen, but where do we get it? So grey hydrogen is the traditional approach, where we're developing it straight from fossil fuels. Turquoise hydrogen from natural gas. Green hydrogen really from as I've said, mostly wind and solar. And then yellow or pink, where we're doing nuclear energy, or a lot of this, as I said, for blue hydrogen, we're talking about carbon capture and storage. Now, the issue there is how effective that is. And so there's, as I've said, quite a bit of a pushback with blue hydrogen, saying it's not all of that it's made out to be. And so really the gold standard, no pun intended, is green hydrogen from renewable energy. And so, yes, the market today is small, and most of the hydrogen is from other factors, but we'll talk about how we see this market evolving. And so here's a little bit around the ecosystem and the value chain. And so you can see here that what we have here is large amounts of power being put through an electrolysis process, producing the hydrogen, and then being able to convert that or refine that. And so one of the real challenges we face as we go through this massive change for all of humankind, and this fifth energy transition is a largely logistical one. Certainly the technology challenges around solving some of the complex scientific issues, but also the logistics around new infrastructure for distribution and storage of hydrogen. And so there are already 2 hydrogen fuel cell cars on sale in the world. So Honda make one, Toyota make one. And so you can see this is not all pie in the sky in the future, but it's around how do we create the infrastructure to allow rapid scale or mass rollout of this. So you can see this is really the flavor of the month. And so there's a large amount of hype and excitement around green hydrogen, and a huge amount of new capacity being announced, and ambitious targets around investment in green hydrogen. And so really it's around, is this all tangible and real? And our view is that we certainly do see the market demand for this. And so obviously all these projects will have to go through the bankability process and phase, but we have seen a number of those already in construction and on the go. Obviously, this is a long-term thing, and so we are really seeing some of our modeling has shown that by the year 2030, we thought that green hydrogen would reach the tipping point of being the lowest cost option in its application compared to alternatives. But actually, since we did this modeling about a year ago now, we've seen that pull forward quite dramatically. And so we'll talk about what is some of the factors that have led to this tipping point of when green hydrogen becomes commercially viable much sooner than we previously expected. And so you can see a large amount of projects, and here's the ecosystem of all the companies around the world that are either developing projects, involved in the value chain, and involved in the development of these projects. So I will say Africa, and specifically South Africa, has a unique natural endowment to be able to benefit from the green hydrogen economy. And so what really is the competitive advantage here? Well, it's 2 things. One is logistics. Well, probably 3 things. Logistics, and here we're at the southern tip of Africa at a bit of a disadvantage. The second is the political and legislative and incentive framework to be able to fast track these projects. And then the third is our natural resource endowment. And so and here's the good news, is that we really do score very highly in that part. And so the economics of these is really dependent on how you can utilize your utilization rates for your capex. And so by that I mean if you're putting in large solar and PV installations to be able to drive these electrolysis units, you want that to be as consistent and as high as possible. And along the entire west coast of Southern Africa, so Namibia and the Western Northern Cape, you have ideal conditions. And so you have large parts of daylight, a lot of sun in the daylight, and you have nighttime winds. And so that gives you the double impact of being able to utilize your electrolysis capacity to the full extent. And so really, South Africa and Namibia have a great natural endowment around our renewable energy potential for that. There are others like Kenya and other parts of Africa, North Africa specifically, that have similar, but this is really for us to capitalize on that natural resource endowment that we have. And so this is a bit of our modeling around how we see the market evolving, and really over 500 million tons a year is what we see as the potential, where green hydrogen is going to displace other forms of energy. And so be that coking coal, be that other non-renewable forms. Let me go to this graph, which is where I talked about this tipping point of economic viability. And so, as I've said previously, when we did the study, we update this annually. When we did this last year, we thought it was just after 2030, 2031 that our modeling has seen the green hydrogen costs come down below some of the other alternatives. Actually, as I said, we see that now, and in some instances during 2022, we've seen green hydrogen be cheaper at some points, and so we really do see that around 2025 now, where green hydrogen is cheaper. So what's driving that? It's let me go to the slide. It's three things: renewable cost, electrolyzer capex, and the price of carbon. And so we've seen here's a bit of data around how those have evolved over time, where a renewable energy cost has come down by order of magnitude from even 10 years ago, and we do see that that trend continuing. Obviously, we've seen some uptick with inflation in the last year, but the long-term trend is there, that renewable energy costs are coming down significantly as economies of scale and manufacturing scale develops in these. And so that's both wind and PV we see. Secondly, around the electrolyzer capex, and so that coming down as well, and continuing to drop. And then obviously the price of carbon does not impact green hydrogen, but it impacts the competitors. And so whether that's grey hydrogen, whether that's other fossil fuels, we are seeing carbon pricing happening. And so how does that impact us here in South Africa? Well, obviously in Europe, it's an actual cost, but we do know that the European Union has instituted and there is legislation in force now around a carbon border. And so from next year, there will be pricing for the difference between the EU carbon market and external carbon markets. And so that is phasing in over a 4-year period. So this is real. This is not. This is something we're all seeing, where the cost of carbon is being factored into all materials and energy sources. And so if you see the combination of those, that is really leading to what I've talked about here around that tipping point. So let me then move on to where do we see, so how does this green hydrogen reach its end consumer? And so naturally pipelines are the cheapest option, and there is a lot of work being done about repurposing natural gas pipelines, and retrofitting those is the cheapest, but some technological issues to solve there around using those to bring them to end use consumer. But also we need to solve the long distance tanker issue. And there we see ammonia as part of the solution. So by green hydrogen, I naturally include ammonia as part of the whole green hydrogen sector, as a more stable molecule and being used to where it is more stable to transport. And so regional distribution as well is a factor where we're using other traditional trucking. Then the other thing I wanted to talk about is, so what does this mean for South Africa? And so obviously we've talked about the potential for us to be a supply hub for green hydrogen, given our natural resource endowment. I was at the Commonwealth Heads of Government meeting in Rwanda 3 weeks ago, and there was a number of sustainability initiatives around that, and business initiatives where we talked, and Namibia is really leading the charge in Africa around creating an enabling environment to capitalize on this. And so it's fantastic to see Namibia do that. And I think there's actually a lot of lessons for South Africa around how they've got on this journey to really develop an economy there. But for South Africa, not only being a supply hub, but if you think about a lot of our mining activities, that's really linked to this energy transition. And so the outlook for a lot of our mining sectors is inextricably linked to the energy transition. And so PGMs, I think the large amount of supply or large amount of demand is really linked to autocatalyst or catalyst. And so for us to develop the green hydrogen speaks very much to our PGM industry, where fuel cells are going to be a major replacement source of demand for PGMs as the world moves away from catalytic converters and the demand for PGMs in those. And secondly, all the other tech minerals that we talk about. And so there is a lot at stake for us here. And so I really do believe that putting our collective efforts behind green hydrogen benefits all parts of our natural resources and energy sectors as a country. So I think I've rushed through that, and this has been a bit of a whirlwind tour, but hopefully that's given everyone a bit of a flavor around the topic, and very happy to take questions and move into Q&A at that point.
Quintin, thanks very much. Appreciate it. You have a few minutes. You've cut yourself short slightly, but thank you. Really interesting. A topic very close to my heart and close to a lot of the work I'm doing right now. So appreciate your perspective on it. I'm just looking to see if there's anything in the Q&A, and I don't see any Q&A coming up, and I don't see anything in the chat. So I'm afraid it's you and me. So let's have a quick chat. So what are your thoughts around drivers of adoption in different areas? I have this model that legislative pressure, which comes from social pressure, drives necessary change, but the economics of the application, which is the carbon cost and whatever kind of industrial process you have, decides whether business will go that way or not, or find another solution. Because ultimately, despite my tongue-in-cheek comment about the accounting in the beginning, economics drives everything. So where do you think the different adoptions are going to occur first? It won't happen with a magic wand across the whole of the world, but preferred geographies where this will be driven hard, and those where you think it will take more than the expected timeline to reach. What's your thoughts? What are your thoughts on that, please?
Yeah, Gordon, it's a good point. So I'd say two things on that. One is in which applications do we think the early adopters will be? I do think it's in the as an energy vector in industrial feedstock as the first part. And so green steel production is if you see that happening in the Nordics already. And so I think injecting hydrogen into those furnaces is going to become real. The other is transport. I think transport is going to be another early adopter sector. If you look at Andrew Forrester out of Australia, he's commissioning a whole fleet of bulk super tankers that will run on ammonia as a fuel source. And so I think we're going to see more of that, where ocean transport bulk tankers are going to be using green ammonia, displacing heavy fuel oil and the like. So those are two. I do think the interesting one will be in the passenger cars that you and I and everyone else drive. As I said, now there's this technology race with battery electric vehicles seem to have the early advantage. but there are commercial hydrogen fuel cell vehicles on sale in many parts of the world. Just they don't have as much PR as the battery electric vehicles. So that's going to be interesting to see how it plays out. And I mean, we've seen in South Africa, the other part is these large mining trucks. Anglo American has one as Mogalakwena, and I think that's another area where the early adopters are going to be using hydrogen fuel cells. So there's a few there. The other point is, so geographically, where do we see this? I think two things. One is, it's great that we're starting to stimulate local demand, because I think it's difficult to have an export industry for green hydrogen without at least some local demand. And so whether that's into the petrochemical industry in South Africa and some of plastics manufacturing and using green hydrogen there, I think that's one area. We've talked about in the mining industry itself, where we can use fuel cell technology. But really I think the prize for us in South Africa is as a supply hub into the developed economies, where we can really capitalize on our natural resource endowment, put this on big tankers and send it to Europe. That's going to be really interesting.
There are two other questions I'd like you to tackle quickly before I just want to move into a closing and an announcement by Bushle. Is one of the questions on the chat is from Tumba, and he's basically saying, yeah, he says, now what is your view on why South Africa is falling behind policy or investments? I think there are two questions there. Is South Africa falling behind, and what do you think are the drivers of the rate of adoption in different countries, not necessarily only South Africa?
I'd certainly say Namibia is ahead of South Africa at the moment. Australia, Chile as well, where they've really been driving a lot of research development and experimentation here. So that doesn't mean all is lost. I think there is a lot of good work that's being done to get us competitive, but we do really need the legislative environment to be able to be conducive, and so that's going to be critical. I know there's a lot of work happening, but the investors need certainty around that. So we've seen business take the lead. As you've mentioned, some of the social pressure here, businesses can really, and a lot of industry can really take the lead and lead where others aren't.
Okay. The last one's a technical question. You can very briefly answer it if you can. If you can't, just say no, and we'll leave it. It's a statement from Friedman, who basically is saying, when you transition of energy from one form to the other, you have different efficiencies. So that's a statement. And then he asked the question, so what is the efficiency when converting solar to hydrogen? Sense on that?
Yeah. So again, I'll give an uninformed opinion, and I'm sure there's other more informed. Certainly that you get the energy losses. I will say, if you look at the energy efficiency in a standard internal combustion engine, that's approaching 30-35%, and so that's your benchmark of what you've got to beat. It's not a high benchmark, and so there is the losses in the energy conversions are certainly better than the 30% you get in internal combustion engines. Key is actually the conversion efficiency. The key to the economics is getting as much energy into the electrolysis as you can, and so that's why I've mentioned having wind and solar working in harmony and offset is fantastic, because then you can really get the efficiencies. But I'll plead the fifth as a non-scientist in that matter.
Thank you very much. We'll leave it there. Thank you very much for your presentation, providing a perspective. It's good to see the high-level view, and where the opportunities are. I always believe there's opportunity in everything. Where the opportunities can lie for us individually as companies, and also for South Africa. This is happening. We just have to decide where to get in and to make it work for us. So at that point, I want to move across to Bushle Kakalashe, Bushley's he just wants to share a little bit of information with us, and then I'd just like to say a thank you to everybody before I close. Bushley, you're live.
Okay, thanks, Gordon. Can you see my slide on presentation mode?
Yes, I can.
Okay, many thanks. Good afternoon, ladies and gentlemen. Further to the interesting and timely talks, I would like to bring to your attention the following upcoming SAIM conferences, which are linked to the topics of today's talks and also have a strong ESG theme. They are the second Mine Impacted Water Conference, the 8th International PGM Conference, and the first Southern African Hydrogen and Fuel Cell Conference. So starting with the first one, the Southern African Institute of Mining and Metallurgy, in collaboration with the University of the Witwatersrand through the DSI, NRF, and Sachiche in Hydrometallurgy and Sustainable Development, and Mintech will be hosting a hybrid conference on mine impacted water, including acid mine drainage, in October 2022, with a theme of impacting the circular economy and closing the water loop. The conference will run over a period of 2 days, and this second SAIM AMD themed conference will provide an excellent opportunity for industry, for researchers and other global stakeholders to share their knowledge, for new processes and technologies that can be used to advance the implementation of sustainable solutions to the challenges associated with mine impacted water. So the conference, with its extensive program, will also offer notable keynote speakers and the popular student session, all with the purpose of giving a unique view into novel solutions and industry progression on the issue of mine impacted water. And this conference will take place at Mintech on the 12th and the 13th of October 2022. Moving on to the next one, the Platinum Conference series has covered a range of themes since its inception in 2004 and traditionally addresses the opportunities and challenges facing the platinum industry. So this prestigious event attracts key role players and industry leaders through high quality technical papers and presentations, facilitating industry networking, having large knowledgeable audiences, a global participation, and comprehensive support from industry role players. And the theme for this year's edition is enabling a cleaner world. And furthermore, the conference will have a strong ESG focus. And the conference will take place at Sun City on the 2nd and 3rd of November 2022, and the 4th of November will be for technical visits. And the last one, the primary purpose of the first Hydrogen and Fuel Cell Conference is the advancement of green hydrogen technologies in Southern Africa and the global community by highlighting the power of renewable and sustainable technologies and addressing the emerging challenges through the exploration of fuel cells, hydrogen storage, and hydrogen generation by way of engagement with industry, academia, and government. The conference will provide a platform for high-level exchange and networking opportunities with various experts in the field. And the theme for this particular conference will be from fundamentals to accelerated integration. And this conference will take place in the Western Cape between the 25th and the 26th of April 2023. So, ladies and gentlemen, in an event of questions, kindly contact the SAIM team and they will relay the questions accordingly. On that note, I would like to thank the organizers of this workshop for giving me this opportunity and looking forward to seeing you at the aforementioned conferences. Over to you, Gordon. Thanks.
Bushley, thanks very much. You give me a minute to close out, and I have actually two sentences to everybody. Thank you very much for attending this webinar, and we really look forward to your support of future events. There's a solid program of webinars, so keep your eyes open on your email to see what's coming. And then the last statement, please take care, please stay safe as we contribute to the sustainability of our nation. Thank you very much, everybody. And we will consider this conference now closed. Thank you very much.